Let me write down the definition. A rational function is just a function that is a quotient of two polynomials. Okay? So definition. A rational function is a function that can be written in the following form. So in the form f of x equals p over q, where p and q are polynomials. And then, of course, q is not the zero polynomial. Okay, so q of x is not the zero polynomial because then, what are we doing? All right. So these are the type of functions that we want to study now. So, for example, an example of a rational function would be x plus 2 over x squared minus 4, for example, something like this. Okay. This is just a fraction where the top is a polynomial and the bottom is a polynomial. And our job is to study these functions. In particular, ultimately, what we want to be able to do is to graph functions like this. Okay, just like what we did with polynomials. That the whole point is to be able to sketch the graph. All right. Now there are some sort of things that we need to take into account because now these functions are not as nice as polynomials. Like for example, polynomials, the domain is all real numbers, right? You can plug in whatever you want. Now, for rational functions, that's not always the case. For example, let's find the domain. What's the domain of this function? So we need to skip 2 and negative 2, right? So remember, here now, we want to make sure that the bottom equals to 0. We ignore that, right? So this happens at plus or minus 2. So these are values that we don't want. So if you think about a picture of the domain, you need to exclude these points and then everything else is fine. So the domain here is negative infinity to negative 2, union negative 2 to 2, union 2 to infinity. Okay? So all of a sudden now there are two values that we need to worry about. For polynomials, we didn't need to worry about any values. Now here, we need to worry about these two numbers, negative 2 and 2. So another question, so by the way, to say here, remark, if you want to find the domain of a rational function, all you have to do is find the values that makes the bottom equal to 0 and then you exclude them. Okay? So domain of a rational function, P over Q, is the set of all real numbers with a set of all real numbers except those for which Q of x equals 0. Okay? So to find the domain of a rational function, just solve whatever makes the bottom equal to 0 and remove that from the real numbers, and then that's your domain. Okay, so let's go back to our example. So given this function, the domain is everything except 2 and negative 2. So another question is, okay, I know I cannot plug in negative 2. We cannot plug in 2 to this function. But we can actually plug in values that are very close to it. And then another question to ask is what happens to the function. For example, what happens if I plug in 1.9, 1.99, 1.999, and so on? I'm not plugging in 2, but I'm plugging in stuff that is getting very, very close to 2. What happens to f? What happens if I plug in 2.1, 2.01, 2.000001? Okay? What's the behavior of the function around this point? This is what I want to know. Okay? So when x approaches 2, what's the behavior of f? Similarly here, when f approaches negative 2, what's the behavior of f? Do you understand the question that we're trying to ask? Okay. So we write that down. So we have this, and then question. What is the behavior of f when x is very close to 2 and also -2. Okay? So in other words, what I want to know is when x is approaching 2, now when x is close to 2 or approaches 2, now there are two ways on understand the following. If you think about the graph of this function, so here is 2, here is -2. These are forbidden values for the graph of f. So you have to think of this as this line right here, these lines, the line x equal 2 and the line x equal -2, they are forbidden for the graph of f to cross them. Okay? Whatever the graph of this function is, they cannot touch these two lines just because the function is not defined. If you cross this line, you're saying that it's defined at 2. You understand this? So this is like a wall, like a barrier for the function. So if you want to get close to 2, now you need to tell me how you're getting close to 2. Are you getting close to 2 from this side or from this side? Because there's a wall here that you cannot pass through. You understand what I'm saying? So it's not just getting close to 2. You need to tell me how you're getting close to 2. So x approaches 2 from the right. So it will be this right here. Okay, we're getting close to 2 from the right. So with numbers that are bigger than 2, or x approaches 2 from the left. That would be, okay, let me change colors. It would be like this, and then this one would be like this, okay? So whenever we say we approach 2 from the right, we have a notation for that. We're going to use the arrow notation, okay? Here we write x approaches 2, but this means x is getting close to 2, approaches 2. To say that we're doing it from the right, we're going to put a little plus on top, okay? So when you see this, this means that x is getting very close to 2 from the right, with numbers bigger than 2, like 2.1, 2.01, 2.001. Those are the kind of numbers that you should be thinking about. Okay? Close to 2, but bigger than 2. Okay? So in particular, this means that x is close, but it's bigger than 2. And then from the left, what do you think we are going to use as a notation? With a minus, okay? So we put x approaches 2, but then we put a little negative on top, okay? This just means that we're getting close to 2 from the left. In other words, with numbers that are less than 2. Think about 1.9, 1.999, and so on, okay? Those would be the kind of numbers that you have in your mind when we talk about the situation. So the question that we're asking is, when x is close to 2 from the right, what can we say about y? When x is close to 2 from the left, what can we say about y? Okay? So the question is, when x approaches 2 from the right, what happens to y? When x approaches 2 from the left, what happens to y? Do you understand this? And then we want to say similarly for -2, okay? Similarly, when x approaches -2 from the right, what can we say about y? When x approaches -2 from the left, what can we say about y? Okay? This is the type of question that we want to answer now. Okay, so I could show you the picture of the function and then you answer the question, but the whole point is doing it without the picture because we want to use this information so that we can graph the function. So it really makes no sense if I show you the picture beforehand. So let's use what we know. Let's analyze this algebraically. Okay? So what do we have for the function? So f of x equals x plus 2 over x squared minus 4. Okay? So when you analyze a rational function, the first thing that you should do is factor everything. So let's do that. Now be careful. Don't simplify because if you simplify, you're going to change the function. Okay? So I'm just going to factor. This is x plus 2. This is x minus 2. So I want you to understand that if you simplify the x plus 2, you're going to get a different function. You get the function 1 over x minus 2. That's not the same as our function. because 1 over x minus 2 is okay with x equals -2, but this function is not. Okay? So they are not essentially the same. So don't simplify just yet. There will be a point at which we simplify, but not now. Okay, so now that we have it like this, let's analyze. So since we are not going to look at the graph because we don't know the graph yet, then the other thing that you can do is start plugging in some values and explore and see what happens. Okay, so let's create a little table of values and then let us hopefully draw some conclusion. And then we're just going to reason through it. But first, I want you to see the values. So I'm going to pull up Excel in here, and then let's do some tables. All right, so we want to get close to 2, okay? So we want to get close to 2. Let's see. Why are you so slow? Okay, so view, let's make it bigger. Okay, so I'm gonna put here the x values, and then over here we're gonna look at f of x. Okay, and then our target is 2. So first, let's do it from the left. So let's do, I guess, 1.9. Then we do 1.99. Then 1.999. I'm gonna do like 4 values. That should be more than enough. Everybody okay with this? So once we're getting closer and closer to this number 2. Now let's do it from the right. So let's say 2.1. Then we're gonna do 2.01. Then 2.001. And 2.0001. And so on. Okay. So now we're here. Let's go ahead and let's calculate the function. So the function was x plus 2 divided by, and then, okay, I'm gonna use the factor version. And then divided by, and that will be x plus 2 and then x minus 2. And then I need to put another pair of parentheses. And I need to tell it to multiply. Okay, so we get our output there. Yes?
You would put the equation wrong. It has 2 of the x's there on the next row.
Say that again?
2 of the x's there are the row.
Oh, I clicked C6.
Yeah,
should be 6.5, C5. There. Okay, good. Thank you. All right, so let's just drag and drop. Now we know that at 2, right, we have an issue because we know that's division by 0, so we know it does not exist. But then again, what we want to do is make a conjecture of what happens when we're getting very close to 2. So again, we know at 2 the function is not defined. But then the question is, what can we say about, the behavior of the function? So let's see. Let's look at it from the left. When we're getting very close to 2 from the left, that means with numbers less than 2. What do you see the y values are doing? Let me center this, make it a little table. So what do you see the y values doing when we get very close to 2? Yes? So what can you say about the y values? Do they get close to something specific? Yes? So it looks like they're getting smaller and smaller and smaller non-stop, right? For example, if I put more 9s in here, then you're gonna get a more, these are smaller numbers because super negative, right? So it looks like a graph is gonna go down to negative infinity. Do you understand this? I mean, you can keep putting more numbers to see it. And now, and on the other side, what happens when we get close to 2 from the right? What do you see? What happens to the y values? What happened? Are you sure? So they're getting bigger and bigger, right? So notice that here we're very close, 2.001, and then we're already at 10,000. If I put more zeros here, then this is gonna change more. Do you understand this? So it looks like when we get close to 2, there's two things happening. When you get close to 2 from the left, it's gonna go down to negative infinity. If you get close to 2 from the right, it's gonna go up to positive infinity. Do you see that from this little table? Okay. So let's put it there. Let's put it here. Okay. Let's see, can I make it bigger? So that's good enough. So from here we can draw some conclusions. For example, we are analyzing what happens around x equal 2. So around x equal 2, we can see this part right here is what happens when x approaches 2 from the left. We can deduce that the values of y grows. So they decrease without bound. So y decreases without bounds. And a fancy way of saying this is y approaches negative infinity. Okay, just keeps going down non-stop. And then over here, this is telling me that when x approaches 2 from the right, by looking at the values, then we see that y increases without bound. Okay, and then we write this as y approaches positive infinity. In other words, if you think about the graph, what's happening here is the function is doing this, and over here the function is doing this. Do you understand this? So when it gets close to 2 from the right, from the left, the function has to go down without bounds. Remember, you cannot touch this line. It's forbidden. It's like a wall. Okay? But then it goes down, so it has to go down non-stop. And then if you get close to 2 from the right, it goes up non-stop. That's what we are observing from the data. Okay? Let's try to see if we can analyze that. You know, what if you didn't want to rely on the table? Okay? How can we analyze that? Well, if you're very close to 2, what will this function approach to? So when x approaches 2, well, let's say we're doing it from the right. So let's do this analytically. So this one right here, we have the function f of x, which is x plus 2 over x plus 2 times x minus 2. So when x approaches 2 from the left, remember this is telling you that x is less than 2, but it's very close to it, okay? So if x is very close to 2 from the left, what happens to the top of this function? What does it get close to? The top is the expression x plus 2. If x approaches 2, what does x plus 2 get close to? 2 plus 2, which is 4, right? If you give me a number that's very close to 2, then when you do plus 2, you get something that's very close to 4. Does that make sense? Like 1.999, then you're going to get 3.999, and so on. So the top is getting close to 4. Okay, that's okay. How about the bottom? Need more space. Let's see. Okay, not right here. So when x approaches 2 from just need a little bit more space, so let me move it. Okay, so when x approaches 2 from the left, the top gets close to 4, and then the bottom, the first factor again gets close to 4, right? And now what happens to the second factor? It's an x minus 2. What happens when x approaches 2? That factor is close to, what is it? If x is very close to 2, what can you say about x minus 2? It's close to 0, so it gets close to 0, right? So now here you see that we have a number on top, and we're going to have a 0 in the bottom. And as we saw last time when we were looking at 1 over x, what happens when you have a number and the denominator keeps getting smaller and smaller and smaller? What happens to the whole thing? It grows very big. Now, if the top is positive, then you grow up. I mean, if the whole thing is positive, you grow up. If the whole thing is negative, then it goes down. Okay? So, the thing is that this is a number over 0. So we know this is going to be some sort of infinity, either positive or negative infinity. So this is telling telling me, just by looking at this, that my function is going to either go up or down when I get close to 2 from the left. Let's figure out which one of the two is it. Is it up or is it down? Well, the sign of this will tell us. Remember, this is just a notation to say the top is close to 4, this bottom, this factor is close to 4, and this one is close to 0. So this is a way of saying this is very tiny. This is not exactly 0. You understand this? Because you're getting close to 2, so you're not at 2. So this is a way of saying this is very tiny. Now I want to know if this tiny with positive or with negative number. So is this 0 point something or is this negative 0 point something? Do you understand this? Because that's going to tell you where you go up or down, where you have a positive or a negative spin. And for that, you analyze the sign. So if x approaches 2 from the left, what do you know about x? It's less than 2. Therefore, what do you know about x minus 2? It's less than 0. So that means that this guy right here, these tiny numbers are with negative numbers. So you're doing 4 divided by something that's going to be very tiny but negative, so this is going to be negative infinity. That's how you can deduce that it goes down without having to do a table of values. Do you understand this? Just analyze the sign, okay? If you see a 0 in the bottom and a number on top, you know it's either positive or negative infinity. Which one is it? Analyze the sign of the factor. Okay? So in other words, the signs here are positive over positive times negative. That's a negative, right? So this will give me negative infinity. That's how you see that. And now the other one, again, the same idea. You have f of x equals x plus 2 over x plus 2 times x minus 2. This time we want to see what happens when x approaches 2 from the right. Okay, the top's still a 4, and this one's still a 0. But how is this 0? Is it positive or is it negative? So these tiny values, are they positive or negative? Well, this means x is bigger than 2, so x minus 2 is positive. So this one right here is a positive thing. Remember, when I write 0, it means something tiny. I don't really mean 0. Okay? It's approaching 0. That's what I mean by writing that 0 there. So I know that this would be a positive infinity because the signs are plus over plus times plus, which is plus. Did you understand this? Because, typically you don't do this table of values. Like you don't sit there and start computing things to see what happens. You just do the sign analysis. Okay? Very quickly. What happens around the point. All right? So that's the behavior around 2. So we solved the mystery around 2. How about negative 2? What happens around negative 2? So around negative 2 is a slightly different the situation. We could do table of values, but I don't want to waste too much. Actually, I want you to see. So let's do it around negative 2. So you can see, and then I'll tell you how you figure that out without relying on the table of values. So this time we want to get close to negative 2, right? But therefore, we need to do this with negative numbers. So let's see, I want to do it from the left. That would be, I have to change all of this. So negative 2.1. So it will be negative 2.1, then negative 2.01, then negative 2.001, negative 2.0001. Okay. And then here we do negative 1.9, negative 1.99. By the way, this that you are seeing here is really the concept of limit, which is the first thing that you study in calculus. Calculus 1, you study this notion of limit. That's what we're doing. Right? We're looking at the limit as x approaches negative 2. Okay? That's what we're doing here. Okay. Can you make a conjecture here? What do you notice? Very good. You see, no matter how close you get to negative 2 from either side, if you do it from the left, it looks like the numbers are getting closer and closer to negative 0.25. You see, negative 0.2499. So keep getting closer. What's going to happen is you're going to have a bunch of 9s showing up. So it gets closer and closer to negative 0.25, negative a quarter. And when you do it from the right, we observe the same sort of behavior. Over here, we're a little bit far away, but the moment you start getting close to -2, we start to see the -0.25 showing up, and then 0, 0, 1, and you start getting closer, it will just be a bunch of zeros, -1 at the end, and so on. If you don't see this yet, then just put more values until you convince yourself. Okay? So the point is that now you can see that the behavior here is different than what we had before. Before we had an unbounded behavior going positive or negative infinity from one of the sides, but now here it looks like both sides are going towards the same place. And this time this is a number. This is not infinity. Do you understand this? Okay? So, but there is something special about that -2. What's special about -2? Why do you think this is happening? What's happening at -2 that is not happening at 2? Can anybody tell me? So why do you think we are seeing this behavior which is radically different from the one above? What's the difference? Because both those points are forbidden. They are not in the domain. They made the denominator equal to 0. But what's the difference between 2 and -2 in this problem? They're both zeros, but there's a difference.
Is it because when you plug in -2, the top becomes 0?
Exactly, because -2 happens to be a 0 in the top also. So if you think about evaluating the function when you're close to -2, remember, it's not really -2, so you could actually cancel this, right? So if you're not equal to -2, if you're -1.99 whatever, this will cancel and you will always get 1 over x minus 2, whatever that is, regardless of where you are to the right or to the left. So that's why you're getting consistently the same thing, okay? And what that 1 over x minus 2 gets close to? It gets close to a quarter. If you get to negative a quarter. If you get close to -2, 1 over x minus 2 gets close to -1 over 4. And that's a -0.25 that you see, okay? So that's the difference, that you can cancel the x plus 2. Here, even if you wanted to, you cannot get rid of the x minus 2, but here we could simplify, okay? So that means, so first of all, here we see that as x approaches -2 from the left, the function f approaches -0.25, and here we see that as x approaches -2 from the right, the function f also approaches -0.25. So we say this, that when you're close to -2 from either side, so if you don't write anything here, we're saying from either side, right or left, the function f approaches -0.25. So what does that mean about the graph of the function? We still cannot plug in -2, but if you're close to -2, then the function is getting close to -0.25. So what do you think is going to happen at that point? Our graph has to get close to this point, regardless. So what should we have in there? A hole. You understand? It has to be a hole because the function is not defined at -2. You cannot plug in -2. Cannot. It's not part of the domain, right? But around -2, everything is fine. So that's what it means to have a hole. So here we have around 2, we have an infinity behavior, right? And then here what we just have is a hole, okay? And what's the difference? That this one comes from a factor that could have been cancelled if we were to simplify, and this one comes from a factor that cannot be cancelled, okay? That's how you determine the two. So what this means is that this guy right here is a hole in the graph. And this hole happens at the point -2, -1 over 4. You okay with this? All right. So note, of course, what if you didn't do a table of values? Well, then you do the simplification process. Because if you want to analyze this function when x approaches -2 from either side, it doesn't matter. This means in particular that x is not 2, okay? X is different than 2. So then I have the right to cancel this, and then this function is going to get close to 1 over x minus 2. Should be a 2. And then 1 over x minus 2, of course, is negative 1 over 4. Okay? So, moral of the story. When you want to analyze a rational function, you factor everything. Before you cancel anything, go ahead and write down the domain. Okay? Because if you cancel here, you're going to miss the fact that negative 2 is a problem. So you're not going to see the whole. Okay? So write down the domain. Now you know 2 and negative 2 are not good. After that, cancel as much as you can. And look at the reduced expression. Now here, whatever 0 remains in the bottom, that's going to have the infinity behavior that we saw. If a 0 disappears from before, like here, we had a negative 2, and now disappears, that means you have a hole at that x value. You understand this? If something cancels and it's gone from the bottom, you have a hole. I'm saying it's gone because if you have something like this, okay, you can cancel this, but it's not gone. You still have your negative 2 showing up down there as a 0. You will still have your infinity behavior. Okay? So, that's why if you cancel and then that factor disappears from the denominators, then that's how you know that you have a hole. Okay. Did you understand this? Okay. So that's how you figure out the behavior of the function around those forbidden values, which are the ones that are not part of the domain. Okay? Now, this has a name. It's called a hole. Okay? Nothing fancy about that. Now, we have a name for the line x equal 2. This is a hole. How do we call this line? Who can tell me? This is called a vertical asymptote. Okay, so what's a vertical asymptote? A vertical asymptote is a vertical line for which when x gets very close to it, the function shoots to either positive or negative infinity. Okay, so if you see that the function is going to positive or negative infinity in at least one of the sides of the line, we call that a vertical asymptote. Okay, and rational functions, they come with vertical asymptote most of the times. So when you're graphing this, your first job is to find all possible vertical asymptotes. So let me define this. And now here we can exactly see what's a recipe to find vertical asymptote. If you're going to have a vertical asymptote, that's because the denominator becomes 0. Okay? And where do you find it? The first thing that you need to do is simplify as much as you can, because if you don't, you may introduce a hole. And you may confuse a hole with a vertical asymptote. Okay? So make sure that you have it in lowest terms, and once it's in lowest terms, find the zeros at the bottom, and that will give you the vertical asymptote of your function. Okay? All right, so definition. This is a notion of vertical asymptote. And then the statement is we say that the line x equal a is a vertical asymptote of f. So I'm going to abbreviate vertical asymptote from now on as VA. Okay, it's a vertical asymptote of f if f of x increases or decreases without bound as x approaches a. From at least one of the sides. It doesn't have to be from both. But if at least one of the sides we see that the function is going to positive or negative infinity, then that's it. That's what it means to have a vertical asymptote. Okay? All right, and then the theorem is and then I guess let me define what a hole is. So that's number 1, then number 2. The graph of f has a hole at x equal a if first of all, if f is not defined at a, if f is not defined at x equal a, and when x approaches a, f of x approaches some fixed number. Okay, that's what it means. That's what tells you that you're going to have a hole. For example, here we saw that -2 is not in the domain, so the function is not defined. But when you get close to -2 from either side, our function is actually getting close to a fixed number, which in this case was -0.25. Okay, that's how you know that you have a hole. I mean, there's a definition, but to actually find holes and vertical asymptotes is just about finding zeros at the bottom. So let me write the statement. So theorem. So let f of x equals to p over q be a rational function in lowest terms. So do you know what do I mean by lowest terms? What does this mean when it's saying lowest terms? It means that p and q, they have no common factors. Okay, so you simplify as much as you can. If they have something in common, you need to simplify first. So let f be p over q be a rational function in lowest terms. So i.e. p and q have no common factors. So when this happens, then x equal 8 is a vertical asymptote of f if and only if x equal 8 is a 0 of q. Okay? So in other words, if q of a is equal to 0. So that means that if you want to find vertical asymptote, just reduce your fraction, your rational function, and then find the zeros at the bottom. Okay? That's how you find vertical asymptote. So it's very straightforward. And then, how do we identify holes? How do we know that we have a hole at x equal 8? If a happens to be a 0 at the top as well, and then after simplifying, it's no longer a 0 in the bottom. Okay, so it disappears from the bottom. So I guess it's number 1, then number 2, x equal 8 is a hole if a is a 0 of p and q. So what you say is a hole if a is a 0 of p and q. Let me say here before simplifying. Okay, before simplifying, and after simplifying, it is no longer a 0 of q. It is no longer a 0 in the denominator. In other words, if the factor disappears, okay? Like what happened for us, that the x plus 2 was gone, that means -2 was a hole, okay? So let's see, let's do some examples. I'm gonna give you some rational functions. I want you to give me vertical asymptotes, and if there are any holes, to locate them, okay? To identify them and tell me what the location of the hole is. By the way, if you have the hole, you know the x is at that point when you see that the factor disappears. How do you find the y? So how did we get the -1/4? That -0.25. How can we find that? What do you do? But remember, that's because you can simplify, so this becomes 1/x minus 2. So if you want to know the location of the hole, you know the x, which is at -2, but the y value you plug into the simplified version, okay, to get the y. That's what it gets close to. So when you graph, you need to know x and y, okay. So example, and you find the vertical asymptotes of f. Also determine if there is a hole. Okay. So let's see. f of x equals x squared plus 5x plus 6 over x squared minus 9. And then let's do f of x equals x minus 1 over x cubed minus x. Okay, so let's do this. So here we have two rational functions. Our job is to figure out the vertical asymptotes, and if there are any holes, we also need to find. The first step is that you need to factor completely. Okay, so let's factor this. So the top, we can factor it. That's x plus 3, x plus 2. In the bottom, we can factor this. That's x plus 3, x minus 3. Okay, and we factor so that it's easier for us to find zeros. Again, here the whole point is to know what the zeros are. Okay, and if you can factor, then that makes it very easy. So, all right. So we immediately see that this is not in lowest terms, right? So if you want to find vertical asymptotes, the first thing that you need to do is write in lowest terms. But before I do that, we realize the function is not defined at 3 or negative 3, so we need to say what happens at those points. Let's see. You see that the x plus 3 will cancel and this reduced to x plus 2, x minus 3. So what does this mean about negative 3? So that means that we found a hole. And where is the hole? So we found a hole at x equals negative 3. Namely, what's the point? So that would be the point negative 3, comma. How do you find the y? You have to plug into the reduced version, right? If you put negative 3, what do we get? Negative 1 over negative 6, so that's 1 over 6. So that means the point negative 3, comma 1 over 6 is going to be a hole. If you want to graph this, you need to have a hole at this location. Does that make sense? Okay, so now that we have the hole, we want to find the vertical asymptotes. So now, to find the vertical asymptotes, what do? We look at the reduced version, and then, like the theorem says, just look at the zeros at the bottom. So what makes the bottom equal to 0? 3. So a vertical asymptote is a line x equal 3. Do you understand this? Yes? Now, if you want to graph, all you need to know is if you are to the right or to the left of 3, what's the function doing? Is it positive or negative infinity? Well, that you do a sign analysis. For example, to the right of 3, let's write the behavior. When x approaches 3 from the right, what can you say about y? Is it positive? And we know it's infinity. That the question is it positive or is it negative infinity? Which one of the two is it? This is what we want to figure out. Well, if you approach 3 from the right, what does that mean about x? Is it bigger or less than 3? It's greater than 3. So it is positive or negative? It's positive. So positive over positive is positive. So that's a positive infinity. Do you understand the sign analysis? And then similarly, if you're getting close to 3 from the left, what's happening? In this case, x is less than 3, so x minus 3 is a negative, right? So you have a positive over a negative, that's a negative, so that's negative infinity. So when you graph, you already know that this is the line y equals 3. Your function is going to do this to the left, it's going to do this to the right of 3. Okay? At least that portion of the graph, you get it done. Questions? All right. And then, how about the last one? Can we factor this? Can we factor this? So here we can do, so the top is okay, and then here we can take out an x. You get x squared minus 1, and so we can keep going. So we get x plus 1, x minus 1. Yes? All right. So this time, once again, we do see that this is not in lowest terms, so there are some simplifications that can be done. So we can simplify here the x minus 1, and we obtain 1 over x times x plus 1. So immediately, once we simplify, what do we see? There is a hole. What's the hole? So there is a hole at x equals 1, and what are the coordinates of this hole? 1 comma. So it will be 1 comma 1 half. Very good. Remember, to get the y value, plug in the simplified version. Okay? All right, so we know the hole. Next, we find the vertical asymptotes. How do we find the vertical asymptotes? In where? In where? In the reduced version. Okay? So for the vertical asymptote, you just have to solve the equation x times x plus 1 equals 0. So we get x equals 0, x equals -1. So we found two vertical asymptotes. So you may have more than one vertical asymptote. Okay? So this function has two vertical asymptotes and one hole. Right? Questions? Okay, so that's how you find vertical asymptote. There's another special type of asymptotes that rational function has. They're called horizontal asymptotes. Okay, so I guess we'll talk about that next time. And then once we know how to find the asymptotes, then we can start putting together the picture to graph rational functions.